Thank you, Tom. I'd like to thank the cryospheric section for honoring me with this opportunity to do two things. One is to wear a tie when I am at AGU, which I believe this is the first time in 28 years or something like that, 27 years. And the other is I get to talk for 45 minutes, which I was accused once of picking up, they used to have a little stand there with the red, green, and yellow lights on there, and I was accused once of picking it up and putting it away. And I think that's apocryphal, but they don't exist anymore, so we don't have to worry about that.
You got 46 because I gave you an extra minute.
And I've got an extra minute, so all right. First, I have a cold. I have a one-year-old granddaughter who lives with us who brings me lots of love and germs. So for those of you in the front row, if I sneeze, I apologize in advance. I'd like to talk to you today about a couple of subjects that are near and dear to my heart. One is abrupt climate change, and this is a subject that really got me started in the cryosphere when I was a postdoc. First started as a postdoc with Jean Jouzel and Willy Dansgaard in Paris and in Copenhagen, and I'll tell you a little bit more about that as we go into it. The other topic that's near and dear to my heart is the importance of polar regions for the rest of the world. So what I'm going to try to tell you in the next 45 minutes or so is a little bit about abrupt climate change and share with you some of my thoughts about why I think the polar regions, Antarctica and the Arctic, are so important for the future, and why all of us who spend any time thinking about the cryosphere ought to be well engaged in the current public debate about what's going on our planet. We're in the midst of a climate change. If that's news to anybody in this room, then we need to step out and have a conversation. How climate changes is critical, however, to a whole bunch of issues, including adaptation, including our economic response, including pretty much all the social responses. Everything that we do is really wrapped around, if you think about it, how fast climate is changing. The faster things change, the harder it is to adapt, the harder it is to deal with things economically, to deal with things socially, etc. So when I talk about change, speed kills is an important thing to keep in mind. So understanding and preparing for abrupt change, I think, is critical to how we move forward, particularly as we're in the midst of a climate change today, in a very large one. There is no universally accepted definition of climate change, or I'm sorry, of abrupt climate change, but in general you need three things. You need a fast change. It certainly has to be less than a human lifetime because, after all, it's all about us, right? So we need to think about that. When I was learning climate change, I learned about Milankovitch. I learned about thousands of years, and I was excited by that. Today, as we recognize climate change as a social issue, we need to recognize that changes have to occur on timescales that human beings can get excited about. Certainly less than a human lifetime. And indeed, changes have occurred even faster than that. It has to be a big change in either average or in variability. In other words, you have to be able to notice this. That's pretty clear. And the change needs to seem out of proportion relative to the suspected cause. So an abrupt change is something that, wow, that happened, and I didn't see that coming, or I saw it coming and it just seems to be too big given the small change that occurred before. I tell a little story. I'll take a moment here to tell you this. When I talk about abrupt change, I use my younger brother Tom as an example. Tom's 5 years younger than I am, and when he was sub-0 years old, I used to poke my finger in his mouth because he didn't have any teeth, right? So this was something I would do all the time, and I would torture him because he's my younger brother, and torture away, and then finally he got teeth, and I didn't know this. You know, I'm 5 years old. How do I know kids get teeth, right? So I poked my finger in his mouth one day and a chomp. And he bites down, and he gets this demonic look on his face, which he can still do. And I start to bleed. I can't get my finger out because he's not letting go. And I'm yelling and screaming, and I call for Mom, and Mom comes, and she goes, Tom, and she's trying to pry his mouth open, but he won't do it. So she says, what'd you do to him? I said, well, I poked him. How many times? Once. Tom is a nonlinear beast, right? He accumulated all that abuse. But that one time when he could react, he reacted. That's really one of the ways I like to think of abrupt climate change. We abuse the planet to a certain point, and then it's going to change. Or it soaks up energy from the sun, or it soaks up energy from greenhouse gases, either naturally or man-made. It soaks up that energy, and then it reaches a threshold, and something happens. All right. I'll talk a little bit about, a lot about, a report that came out last year, Abrupt Impacts of Climate Change, Anticipating Surprises. Many of my co-authors are here in the room, and if we get time, I'll put that list up for you. It does follow on from a previous report in 2002 that Richard Alley, a previous Nye lecturer, was lead author on. These are really a couple of the only times that we've really systematically looked at abrupt change. But I think it's something we need to do. We need to keep looking at this. What I found really interesting about this process was that we started talking not only about abrupt climate change itself, but abrupt climate impacts. So the impacts that come from abrupt climate changes. And it's interesting to note that you can have steady changes in climate, steady changes in, for example, sea level. I'll give you an example of that in a second. And or anything in the environment that then can trigger abrupt shifts in human systems and related natural systems. This is important to recognize. You don't just need a big change in temperature, or a big change in precipitation, or a big change in variability to really qualify as an abrupt change. You can have gradual changes that push human systems past a threshold. And that's an important concept because indeed, again, it's all about us. And there are many more human systems that have abrupt thresholds than there are natural systems, at least I believe so. I'll give you a couple examples of that. When we were writing this report, I got a phone call from someone who designs very large air conditioning systems for server farms. Think Google, Microsoft, etc. These are very expensive. They're amortized over 29 years. That's what the federal government allows you to write them off for. And he said, I need to know the average high temperature 29 years from now. Right? So I sent him up the hill to NCAR because it's my best source for the average high temperature 29 years from now. But I asked him, why do you need that? And he said, when we design the air conditioning systems, they have to last for 30 years. Because if they don't last for 30 years, to my clients, that's an abrupt change. If they can't write off the entire cost of this thing, if after 15 years, in other words, this piece of equipment no longer meets their needs, then they've lost a lot of money. So a slowly changing temperature triggers an abrupt change in an insurance or the cost of an air conditioning system if it's not going to last for 30 years. All right? So that's one example of abrupt change. There are many other examples. I think New York City's subway threshold is a questionable example, possibly an example. This is the height of the New York City subway system showing many storm surges over the years. Sandy comes along, tops it. That's a very obvious threshold. Whether or not that was driven by human climate change or not is certainly a question of some great debate. I personally think that given all the greenhouse gases we put in the atmosphere, any change today has got human fingerprints on it, but whether or not Sandy would have occurred with or without that, which is why I put the question mark there. But again, it's another example of a threshold that was reached. Change won't always be obvious. Imagine you're a European explorer. You're on a river in the New World, and you don't know it, but the river's name is Niagara, and you're cruising down the middle of this river. It's a fast river. You're paddling fast. You're making good time. Not suddenly, but you just kind of hear this roar up in the distance. You're not quite sure what that is. You've not heard a roar like this when you're on a river before. At some point, you have a choice. Either you try to get that canoe over to the shore. You realize something bad is about to happen. But long before you make that decision, the decision's already been made for you. You can't get to the shore fast enough. You're going to go over Niagara Falls because you've been out in the river and you've been going too fast. The tipping point in this situation is not so much when you go over Niagara Falls. It's when you miss the chance to get over to the shore. So this gets back to things like, should the precautionary principle be involved here? If you're an explorer in the New World and you're exploring a river, my advice to you is stay near the shore because bad things might be lurking up around the bend. Right? So this is an example of the ways that some of these things can happen and sort of they seem predestined, but in reality, you've passed the tipping point and you don't even know it. Okay. This is all set up, by the way. We are definitely on the edge already. The Earth is more vulnerable to abrupt change today because of human activities, and I have a whole couple of slides of these metrics. We've certainly altered the Earth's energy balance. We've changed climate. There's a whole bunch more of these things. They're kind of fun. We move about 10 times more dirt than all natural processes, a very AGU-like kind of metric. We figured out how to make nitrogen fertilizer back in the 1930s. People got Nobel Prizes for that. We now make we've now fixed more nitrogen fertilizer than all the bacteria on land in one generation. We went from really nothing in the nitrogen cycle to today. I wandered through the poster hall. There were hundreds of posters on the nitrogen cycle. Okay, so we've definitely made a difference there. We make more sulfate than ocean phytoplankton, et cetera. The key here is these glasses down here. As human beings have used more and more of the resources of the planet, we've pushed the ability of the system to adapt to change to smaller and smaller levels. So even a small change now can seem abrupt to us because it can push us over the edge, right? So we've preconditioned the system. Now, how did this happen? Two reasons. There's a lot of us. So we are at 7-something billion here today. People in this room understand the exponential. When you talk in public, people may not understand this. I still have people who see this graph and gasp and go, that can't possibly be right. And I go, well, if there's one thing we're good at as human beings, it's making more human beings. Reason number two, however, which I think is a bigger reason, is use per capita. So as societies have industrialized and life has become better, the amount of energy we need, the amount of food we need, the amount of fresh water we need, all these things scale roughly the same, has grown. To the point now where we have a planet that has a lot of folks who live very well and a lot of folks who don't live very well at all. This is a plot of the per capita, this is in kilograms of oil equivalent, this is just energy use for various regions of the world and for various countries of the world, but I want to focus here on low income, middle income, and high income. So if you want to go from a low income country, and there are many of them around the world, a couple billion people in this position, up to middle income, you have to increase your energy consumption by a factor of 3.5. You have to also increase your fresh water use by a factor of 3.5, and your calorie consumption, and your consumption of minerals and other things that we need in order to make society work. But this is not just a question of that 1 or 2% population increase. This is 350% increase in the amount of energy needed. And if you want to go from middle to high, hopefully this is not aspirational, from low to high, it's 7 times, right? Notice in here China. I'll point out China and India as two good examples here. China has already industrialized tremendously. It's the #1 producer of carbon dioxide in the world. There are still roughly 1 billion people in China who aren't participating in that consumption. And when they do start participating, this number is going to be even higher, right? Look where India is. India is the country we talk about as the next country to industrialize. In order for India to become like Denmark even, you're talking about a 3 to 4 time increase in the amount of energy needed. These are very large numbers. This is what I call the nasty dilemma. We want others to live well, but if they do, the energy, the amount of food, the amount of calories, the amount of bacon, the amount of everything they need is going to be significantly larger. That's the challenge of sustainability. So now let's talk about some abrupt climate changes. I'll start with the past. Abrupt change is a common and natural feature of the Earth's climate system. When I was a graduate student, I learned about, as I said, Milankovitch, et cetera, the gradual kind of climate change forced primarily by the Sun-Earth interaction. When I started to work in this area, we started to recognize it was Greenland ice cores, ocean sediments. I remember wonderful talks about abrupt change, even in, for example, the snails living in the Thames River mud. But at the time, people said, yeah, climate can't really change that fast, right? So I'm going to show you data from a few ice cores here, so we'll actually do some science in this talk. Mostly from the summit cores and then North Grip and Nîmes. So we're going across something in the neighborhood of 5-6 degrees of latitude here. This is the view we have now of climate from a Greenland ice core. In green is the, I believe, North Grip temperature record. It's stable isotopes translated into temperature, but we've also measured all of these changes in other ways, so we know these are temperature changes. But this is a very angry climate, if you will, as my advisor Wally Broker once said, with large changes going on. I've put sea level on here as an example of something that changes more slowly, although you notice there's some fairly large changes in sea level here that are occurring in a fairly short period of time. And I'll loop back to sea level because the intersection between sea level and the cryosphere is a very strong one. But these Dansgaard-Oeschger events were known back in the late 80s. We weren't 100% sure exactly what they were. When I got into this field, I was invited by Jean Jouzel to come work in Paris as a postdoc, and Willie Dansgaard sent me some samples to measure out of the Dye 3 ice core, saying, let's find out how quick these things are. Let's cut these things on a year-by-year basis and see how fast they are. So we got together and measured across the end of the Younger Dryas here. Each of these is a sample, and we measured a number of things, dust and stable isotopes. But I remember sitting with Willie and Sigfus, and I show their pictures because both of these gentlemen were hugely influential in my early career. Sigfus just recently passed away. Willie passed away some years ago. We argued about whether or not people would believe that a 50-year change, that this step in temperature, which is very large, more than 10 degrees C, happened in less than 50 years. We argued and argued about whether anyone would buy into that. We also noted that deuterium excess, which is an indicator of ocean conditions, probably sea ice out in the North Atlantic, changed even faster than that. And when we originally drew the figure, by the way, we had it at 5 years, and we decided no way anyone was going to believe that. It's got to be at least 20 years. So that was where we were back in the early 90s. We were arguing about whether or not how abrupt these things were, whether or not anybody would possibly believe them. The story evolved thanks to hard work by Richard Alley, Jeff Sevinghaus, Ed Brook, Todd Sowers, some excellent folks in Europe working very hard and trying to understand all the parameters that are changing here at the end of the Younger Dryas. We found out that it's not just a question of temperature changes. It's a question of the rate of snowfall doubling in a very short period of time, 1 to 3 years. Methane goes up 50% in a lifetime. Nitrous oxide goes up 10% in a lifetime. These are very large changes. Atlanta to Minneapolis, for example, is 9 degrees. So imagine, you're born in Atlanta. That's the climate you grow up in, and by the time you're an old person, it's more like Minneapolis, or the other. Actually, I prefer the other way around because it'd be nice. It'd get warmer. So we do know that these things are real. We've seen them now in many ice cores. And what we're beginning to find out now is that what we mean by abrupt is, in other words, how abrupt is an interesting question. As I pointed out, we put 20 years for that deuterium excess change in the Dye 3 ice core. The Dye 3 ice core is not shown here, but we have North Grip, GIS2, and NEAM all plotted on top of each other. We can actually see annual layers in here, so we know when the annuals are. And these are markers, volcanic markers, that we use to cross-date the core. So we're not matching the isotopic records up in this case. We're using the volcanic markers and then counting years in between to line these 3 records up. And you can see that across a fairly large area, this is deuterium excess, there's a very systematic excess shift and a lot of common variance throughout this system. So there's very large signal that's going on here. In this case, we think it's the retreat of sea ice. And now we know that this is a matter of 1 to 2 years. So in a matter of 1 to 2 years, there was a very large change in what happened out over the ocean. As I said, the only thing we can think of that happens that fast is a change in the sea ice extents. And that's happening, and it's not just a question of human lifetimes. It's not just a question of decades. It's, as I tell my students now, it's less time than it takes to get through college, right? Which almost gets their attention. If I could bring this down to the amount of time it takes to get to Thursday, which is the new Friday, then I would point out here that recent breakthroughs over the last 5 years or so in analytical systems now allow us to pull these ice cores out, put a stick of ice on a melter, and continuously measure isotopes. All of these were cut laboriously in a cold room somewhere and put on the mass spectrometer. We can now measure these things continuously, and we can measure them rapidly. We could do 5 or 6 ice cores across a transition for something like this in a matter of a couple of days. So the technology is changing, and look for more and more high-frequency data out of the ice coring community in the next several AGUs. The other point I noted here was that, so it's not just deuterium excess, but I noted that the deuterium, which is a proxy for temperature, changed in about a human lifetime. Well, this is not my best slide for this, I apologize, but we now have, again, with the matching up the volcanic events, we can now show that what we thought was a human lifetime is probably made up of 2 events. So there was a warming, a plateau for about 30 years, 40 years, and then a warming again. Such that out of that 10 degrees of warming, it was about 1 degree per year for 5 years. Then it plateaued for about 40 years. And then it went up about 1 degree per year for another 5 years. So a very different view is emerging now. These abrupt events actually have abrupt events lurking within inside them. This is beginning, I think, to give us the ability to understand what really controls these things. But I would point out to you that 1 degree per year for 5 years is 100 times faster than the current warming. We've had about a degree, maybe a little bit more than a degree, over the last 100 years. And we've noticed that. Imagine something that was even 100 times faster than that. This would very, very clearly, 1 degree per year would be something you would absolutely notice. And it's happened many times in Earth's history. And it gets even worse. We've now, when we first pulled out the North Grip ice core, we noticed that this is the bowling warming now, which is about 14,000 years ago, showing another very large warming, about 10 to 15 degrees C. This, in the North Grip ice core, was about 1 year, 1 to 2 years in the isotopic record. We underplayed it. We talked about it. I believe it might even be mentioned in the North Grip paper, but we didn't stress it because, again, we were going, how can this possibly be? It wasn't until we got the NEAM ice core, which shows the same thing. And again, these cores are matched up not by matching up the jump, but by matching up by independently dating these things. But we now know that in northern Greenland, this is not true for southern Greenland, but in northern Greenland, there must have been some threshold in which the atmospheric circulation got to some point and then bam, it changed. Such that you got about a 10-degree change in mean annual temperature in northern Greenland happening in about 1 to 2 years. And we now have replicated that in 2 ice cores. That's 1,000 times faster than the current warming. So this is clearly something that would get all of our attention. I would point out that abrupt change is not just something that occurred in the past. This is, as we were writing the report and as we were talking about the report in public, something that as a scientist I didn't really think about and didn't really consider and didn't really appreciate, to be quite honest, is the fact that abrupt change is happening now. That if we were to go 200 years out in the future and look into the record of today, we would see abrupt change. And those abrupt changes would be just as clear as the abrupt changes that I talked to you about that we see 10, 15, 20,000 years ago in ice cores. Right? There are many such abrupt changes, but let me focus on one of them, Arctic sea ice. I would also point out that groundwater loss is an abrupt change that's happening today, and it's something you very much should keep your eyes on, including many of them, species extinction, ocean acidification, etc. But let me talk about Arctic sea ice. Right? So Arctic sea ice, since the 1970s or so, has decreased by roughly 50%. This is the average monthly sea ice extent in September from the fine folks across the parking lot from me at NSIDC. By any measure, that's an abrupt climate change. In less than a human lifetime, Arctic sea ice has shrunk tremendously, shrunk noticeably, shrunk significantly. You pick your adjective, right? Certainly faster than anticipated. The experts who've been looking at this, who've been modeling this, who've been predicting this is faster than what they thought. This has many impacts on Arctic ecosystems. It has changed shipping routes. It has changed tourism. It has changed coastal erosion. If you are living in Alaska, you know about climate change. It is a reality. It's something in your face. It's something that maybe we don't see down here at 30, 40 degrees north as much, but in the Arctic, this is a very real change, and it's happening, and it's an abrupt change. So when your friends and neighbors, when you talk to them about climate change and you happen to mention abrupt change, you go, oh, was that something that just happened in the past in ice cores? No. It's something that's happening today. It has some interesting implications. There's a wonderful little video from NOAA. If you haven't downloaded this, please do so. This is going to crank up. The oldest ice is here in white. This is ice that's a decade old. It's thick. It's able to withstand melting. I love this because you get to see the circulation of the ocean atmosphere system. You see the icebergs disgorging off here. This is why we're going to Renland to try to measure this. All these icebergs come out here and sink the Titanic and make Leo DiCaprio rich and other stuff like that. But you'll notice that the way the system works, or worked for thousands of years, is that old ice is lost and old ice is reformed, so that this would remain old ice, and so it would be able to withstand warm summers. It wouldn't melt, because you can't melt, meters thick ice in one summer. What happened in 2007, you all know about. 2012, another year. And what you have now is a very different situation. You've got an Arctic Ocean which is largely made up of 1, 2, 3-year ice. And that's very different from an Arctic Ocean that's made up of multi-year ice. 1 to 2-year ice is vulnerable to melting. 1 to 2-year ice is something that can change rapidly. Right? This is a system that has been set up for abrupt change. And I think it's a fairly easy prediction that sometime, probably within the next 10, 15, 20 AGUs, we'll be having a whole session on what happened after we had large decreases in Arctic sea ice. We already do have those sessions, by the way. I would point out that sea ice that's only 1 year thick is something that is very vulnerable. I looked this up. This is Lake Erie from 1973. You have to go back in time to find out when Lake Erie was freezing over in the past. This is Lake Erie in February 27th of 1973. It is 100% ice covered. 2 weeks later, on March, I can't read that. What does that say? March 13th. I should know when 2 weeks later is. March 13th, it's almost completely ice-free. So those of you who grew up in lake ice areas know this. The spring melt-out of ice is a very abrupt thing. And it's abrupt because the atmosphere warms up. It's abrupt because the ocean warms up. It's abrupt because the winds come along and start to stir this up. I would propose to you that we are in a situation now with Arctic sea ice where we're set up for abrupt change. And we ought to be ready for it. And we're not. I would also point out that as the Arctic warms and as sea ice in the Arctic shrinks, and particularly as we start to see ice-free summers, you're going to see what is already a new frontier become even more of a new frontier. There are many studies that do this. This is one from Science in 2007 where they look at, and the density of red here is the density of human footprint measured by a variety of parameters on the surface of the land. There are some places where we're never going to have a whole lot of density. But note the Arctic here. This is an area where we don't have a lot of density, and we can have a lot of density. As time goes by, these areas will get red. As time goes by, people will be moving into these areas. I think it's absolutely fascinating from a sociological point of view that here we are in 2014, and a new frontier on the planet is opening up. New frontiers went away in the 1700s, 1800s, right? Now we have a new frontier. And we get to watch this new frontier be explored. We get to watch this new frontier be exploited. We get to watch the native populations get trampled by other people. We get to watch all of these things happen that we know are going to happen, or at least they used to happen this way, if we don't change the way that we do things. So watch this as well. This is definitely a new frontier. I would also point out that abrupt change is coming in the future as well. And there are many thresholds of interest here. Definitely species loss, marine terrestrial, droughts and floods, oceanic oxygen minima. There are some changes that we talked about in the report that are likely to be large and very important, like loss of permafrost, but probably not abrupt. So I think it's important to recognize that when we talk about abrupt change, we're not talking about all features of the climate system changing abruptly. Some of them do indeed change slowly. Right? So sea level doesn't, well, although I'll talk about abrupt here in a second about sea level. But certainly the melting of permafrost is something that we think probably has brakes on it. Can't happen that fast. But let me focus on sea level rise, because that is the other piece of this that has cryospheric implications. Right? This is a plot from Foster and Rowling in Proceedings of the National Academy of Sciences showing carbon dioxide levels, and we all know we can map temperature onto this as well, and sea level for the last 400,000 years. And this makes a point, this makes a couple of points, that it's not just temperature and greenhouse gases that went up and down for the last 400,000 years, but keep in mind that sea level is very tied to temperature on the planet. And temperature on the planet then being looped back into greenhouse gases. And the reason has to do with the very simple physics here. Part of it is a thermal expansion of water. We all know that. You can't get around simple physics. If you want to try getting around simple physics, try getting up in the morning and denying gravity and see how far you get today. There's also some very simple physics involved in if you warm the air up, you warm the ocean up. When you warm both of those up, you start to eat at the land ice. And the land ice is going to go back into the ocean. What I think is really fascinating about this, and what those of us in the cryospheric community, I think, really need to get the message out, because in my experience in talking in public, almost no one appreciates this out in the public sector. And that is the surprising size of sea level change. All right, I want you to just point out here, the scale here is from 180 parts per million to roughly 280 parts per million and change. We're at 400 today, so we've blown this scale out of the roof. But look at the scale on sea level, 0 to 130 meters. All right, 130 meters is a hell of a lot of sea level change. This, for example, is Florida, if seas were lowered to glacial size. So Florida was twice as large as it is today, back in about 20,000 years ago. Probably, you know, lots of wonderful little beach houses out here that are no longer here. This is Florida if you melt all the land ice. So Florida is either a very large and wonderful place, or it's underwater, depending on natural variability of sea level. Right? When I talk to folks about sea level change, I get ideas like, you know, a foot, maybe 6 inches of sea level change. That's big, right? I'm going to worry about that. And then you go, but wait a minute. You know, if you go back just 120,000, 130,000 years ago, sea level was 15, 20 feet higher. Does that bother you? No, because you're wrong. Because sea level can't change that much, right? So it's very difficult for the average person out there who hasn't thought about the enormous flip-flop of water between the ocean and ice sheets to appreciate just how large these numbers are and how important it is to us as human beings, given the fact that much of the population of the world now populates the coasts. We're expecting sea level rise of about 1 meter by 2100. I've been several NI lectures that have gone into that number, as I don't have to do that. I would point out that if you look at the record of sea level change in the past, and we've looked at this not only in the last transition, but looking back into the Eemian period and beyond, rates of 3 times faster than that are common in the past record. And I would propose to you that 1 meter in 100 years, hard to get people really excited about that, but 1 meter in 30 years is a fundamentally different thing. 1 meter, so 3 feet in 30 years makes a difference. When you buy a house on the beach, right, you get a 30-year mortgage. If at the end of that 30-year mortgage your house is worth due squat, it's a technical term, that's a big deal to you. If at the end of 30 years you can still find some climate denier who's dumb enough to buy your house, right, sell it to them, right? So the speed with which sea level rises loops back to that issue of abruptness. In this case, abruptness may be defined as a mortgage, or it may be defined as how rapidly the federal government can deal with something like federal flood insurance, which isn't very rapid, right? So keep that in mind, that expectation, anticipation is the key that we need to understand if we talk about speed, right? So there are 3 hows when it comes to sea level rise. Actually, 3 hows when it comes to any kind of a change. One is how fast is a change occurring, and that's what I'm talking about now. The second is how far, and we'll delve into that, right? So one of the interesting phenomena that's going on today is there's all sorts of meetings in New York and Miami and Norfolk, et cetera, talking about sea level rise. By the way, they don't really think about ice sheets when they do that, although they ought to be. But it's interesting because the 2050 is about as far into the future as they're willing to go. They're going, okay, we're going to have a couple of feet by 2050, we'll deal with that. Manhattan is right now talking about building a very large, beautiful little dike around the end of Manhattan. Billions of dollars, right? Is that going to stop anything for the long period? Of course not, right? So the question of how far eventually has to be dealt with at some point. The third how that you need to know is how inevitable is sea level. I love this quote, right? Miami Beach Mayor Philip Levine said the city is too valuable to lose, with real estate worth more than $23 billion and tourism revenue over $9 billion. Right? Well, I'm sorry, Phil. West Antarctica doesn't care. what Miami Beach is worth. All right? And this is what we're watching today. We're watching marine-based ice sheets because they're the ones that can change pace. They're the ones that can change us from the 1 meter in 100 years to something greater than that, something even more challenging than that. If you don't know, this is a bedrock map of Antarctica showing that most of West Antarctica, with the exception of some pinning islands out here, are well below sea level. Anything in blue here is well below sea level. I also point out that there's a large chunk of East Antarctica that's lurking in the blue level as well. Why is that important? I've listened to Richard Alley now so many times that I can actually say this. Something called a grounding line exists, folks. This is where ice comes out. It hits a bedrock or even sedimentary hold. It stops there. And this is what we're concerned about. There's many, many sessions here at AGU talking about this. Warm water creeping in, eroding this. And once you lose this point, there's really not much to stop this system from shedding ice. And if you go back to the previous slide, it's not a question of a small little outlet for the ice to come out of. These are hundreds of kilometers of outlets. So the mouth on this system is very large. And what you're missing in this scale is how large this can be. And when you start to lose this system, it can start to shed ice. And, we're not talking about, a meter in a week, but certainly several feet in a matter of in a matter of 50 years is something that we all need to be concerned about. And that's very, very possible given the system. It is a long, slow, losing battle. All right, there's been a lot of discussion, some very excellent modelers and some very excellent scientists, Eric Renaud, Ian Jockin, and their groups have been looking at this. There have been many other papers that have been talked about mechanisms. But we are quite concerned that West Antarctica might have already begun to shed ice and there's no real stopping this thing. That it's just going to continue to do this for centuries to come, and the sea level change that's implied here is of the order of meters. Now that's a slow process, but there are abrupt points within the system. And this is, if you go in and look at the NAS report, you'll see many of these discussed in there. The Federal Flood Insurance Program is a really interesting one. If you follow this, the federal government said, no, we'll make people pay in reality what they have to pay. And then everyone complained, and they said, no, we turned that over, so it's okay. We'll continue to insure you. This Federal Flood Insurance Program could be one of the largest entitlement programs out there if we don't watch out. Larger than Social Security, larger than Medicare and Medicaid, given the trillions and trillions and trillions of dollars of assets we have along the coast. There are issues of property values. These are not likely to just sort of slowly decline as sea level rises. These are likely that people are going to go, oh crap, they have that oh crap moment, and housing prices or the property values are going to drop. Infrastructure. Once you start to see electricity, gas lines, et cetera, begin to be threatened, then it's a big game changer. And many of these communities depend on fresh water nearby, and as salt water begins to intrude, at some point they lose too much of their freshwater wells. So these are all abrupt points that are lurking in there. There's also political tipping points in the system. I love this little article. This is an article recently. South Florida City Council votes to secede from Florida. So these folks down here don't like it that the folks up here in Tallahassee are running the show, and they want to care about sea level. Ironically, as if sea level goes up 17 feet, most of their constituents are underwater. So maybe this is why the folks in Tallahassee don't care about the folks down there, because they know they're not going to be there after a while. It gets you a little bit scarier. This is a plot from David Archer, who was one of the members of the committee. The last time the Earth had 400 parts per million CO2 was roughly the Pliocene, about 2.5, 3 million years ago. On this particular plot, you get something like 20 meters of sea level change. All right, this is and that's only that's a couple of degrees warmer, less than a couple of degrees warmer. 2 degrees C. I keep seeing debates about is 2 degrees C the right threshold for future climate change to avoid dangerous tipping points? Well, yeah, I think it's well below that. But this is the IPCC forecast for 2100. There's really no reason that we in the cryospheric community, I think, can come up with that this point won't start migrating up towards that line. Right? So this is one way to answer the how far question. Another way to answer the how far question, Foster and Rowling looked at this, where they took relative sea level. Now they've converted CO2 into the forcing function. I like this plot because it shows that when you really cool things off, you can really drop sea level by making ice sheets. There's a fairly stable plateau in here of about 14 meters higher than today, plus or minus quite a bit. But that lasts from roughly 300 ppm to roughly 600 ppm. In this particular plot, what it tells us is you get a bunch above 600, 700 ppm, and you're likely to start melting Antarctica, and you're likely to see sea level go up to the roughly 70, 80 meters that it possibly can. We're at 400 ppm today, folks. I'll take bets today that we make 600 by the end of the century. I won't be here to collect, but you can leave it to my kids and grandkids, because I know we're going to make it. Right? So you can have some fun with this, or you can be depressed by this. This is the depressing part. This is why the Pentagon spends more money on climate change than just about any other federal agency. Bangladesh, with 13 meters of sea level rise, is a lot of refugees. And I think if you're paying any attention to the politics of the day, you know that refugee camps are not going to turn out well for us. Right? As I said, you can have a little bit of fun with this. This is the Grand Valley here in California with 13 meters of sea level rise. Depending on whether or not you're a fan of Sacramento, you build a dike or a dam out here somewhere. It's surprising. These are wonderful little plots. You can, thanks to the USGS for all their hard work in putting together a lot of the elevation data. You can have some fun with this. You can continue to have some fun with this. This is 20 meters of sea level rise, so I'm taking the high end of things, which I think is really high, but anyway, this is 20 meters of sea level rise. When I talk in public, I ask folks, all right, what's really important about this part of Florida? Disney World, absolutely. All right? Everybody gets that. It's amazing. No one misses that. I point out to them that Disney World survives 20 meters of sea level rise. And even better, you can sail the Disney Princess almost right up to the Magic Kingdom. Right? So it's not all bad news, folks. This is the one piece of my talk which you will remember. Nothing else probably, but this is it. This is what state class? Delaware. This is Delaware with 20 meters of sea level rise, by the way. It's not really a Delaware anymore, it's a swamp. What was the first state of the Union? Delaware. If you want to remember ultimate sea level rise, all you have to remember is first in, first out. If you can remember FIFO, you can remember ultimate sea level rise. Right? It's amazing. I've had people come up to me 10 years later in a restaurant in the middle of nowhere, look at me and go, FIFO. Right? Try it, it's fun. Oops, sorry, wrong way. So, you can have a little bit more fun with this. Are you not getting through in your conversation with your neighbor about sea level rise? All right? Try reframing the conversation. This is from a wonderful website called Dog Sports, which is if you're into Southeast Conference football, if you're from Europe, I'm going to lose you immediately. Right? In the U.S., there's something called football, and it's not played with your foot. And there's a lot of people in the south of the United States who care about football and who don't care about climate change. Right? But this is from a website from Georgia fans. USGS predicts that if ice caps were to melt completely, sea level would rise by approximately 80 meters. They're right about that. It's amazing to me. If we can get polar ice caps to melt only halfway, sea level will rise 40 meters and the face of the earth will change forever. Now is the time, Georgia fans. Trade in those efficient vehicles for gas guzzlers. Spray some aerosol. Burn as much coal as possible. We can make Florida a thing of the past. I would submit to you that the average reader of Dog Sports doesn't believe in climate change, but framed in this way, they would embrace the notion completely, wholly, and go for it. Right? All right. I'm going to end up with some positive thoughts here. I only got a couple minutes, and I want to finish up here. Because I think that really, in order to get beyond this, in order to achieve sustainability, we have to bring in not just the science side, which we do very well, and the economic side, which seems to drive the decision boats, but we need to start talking about ethics, because I think that that is really ultimately where the answer lies. So I'm going to give you 3 thoughts. Thought number 1, we say we love our kids, but do we show it? All right, we live on a water planet. And on a water planet, the impacts, particularly temperature impacts, come after the causes by 50 years or more because it just takes a long time to warm up water. We all know this in this room. 90% of the extra trapped energy is going to warm the ocean today. We know this. But when we say we love our kids and we're not willing to look more than one generation out into the future, in other words, when one generation is not willing to set aside short-term profits to deal with the benefit of their children, you're never going to solve this problem because we live on a water planet. Right? And you can't get around the fact we live on a water planet. So there's an intergenerational equity. If we love our kids and we actually act like we love our kids, we can start to deal with this problem. Thought number 2, in order to solve the problems we've been talking about, you got to control population. What's the number one way to do that? You ask any demographer, they're going to tell you the best and most lasting way to do this is to empower women, economically and politically. Around the world, women are second-class citizens. Even in the, I asked my class this, who's the first female president of the United States? I haven't had one, folks, right? Until women participate in the political and economic power around the world, and when they do, they have fewer children. Until that happens, you're not really going to be able to deal with population. So guys, think about it, okay? We can share. The third thing I want to leave you with is you got to care about our shared planet. You cannot have 2 billion people living in poverty so deep that the health of the environment is not a consideration. I'm not talking about wealth distribution flat. I'm talking about the rich have got to care about the poor more than they do on the planet. So in order to achieve sustainability, I've given you 3 ways in which we as a species actually have to grow our butts up and be a better people. We need to actually show that we care about our kids and not just talk about it. Men and women have got to share power on this planet, and the wealthy have got to make sure that poverty is not so deep that people don't care. And that is about the most positive message I can leave you with. Thank you all for listening. I'm happy to take questions.
So we do have time for a few questions, please.
I said nothing. Over here. Yeah.
Last year, many of you may have heard Jim Hansen give not a similar talk, but his own view that the CO2 was rising too fast. Toward the end of that talk, tongue-in-cheek, they proposed that could we adapt to accepting nuclear power? And your views, maybe you heard him talk, we appreciate it.
Yeah, nuclear power is an interesting conundrum. I teach a course on energy and the environment, so I've looked into nuclear power quite a bit. My own personal view on any form of energy is that it needs to be, we need to consider all costs going in and all costs going out. And the problem I have with nuclear power is we haven't really figured out how to deal with the waste. It's too expensive to deal with. In my opinion, creating that amount of waste is not cost effective. So I'm not a fan of nuclear power for that reason. But that's a simple economic reason. Seriously, please. Yeah, to repeat the question, so the question is temperature is also going up and humidity is also going up. At what point does it get so warm that living in the tropics is a losing proposition? I don't know exactly the answer to that. I mean, some of that has to do with human health. Some of it has to do with ecosystem health. It is, I think, as a paleoscientist, I look at the fact that the Earth was much warmer in the past. And I see that it wasn't devoid of life even in the tropics at that time. So there must have been adaptation strategies for both plants and animals at that time. Speed kills, though. So as things happen too fast, can we adapt to that? And I don't know the answer to that. I think that's a very legitimate question. I wouldn't argue that, I focused here on the cryosphere and its impacts on the future. But I wouldn't argue that there's not many, many more very important points, many important impacts that we need to consider. Yeah.
So you said that climate has changed the oceans faster than the past. What would be the mechanism to cause that?
What would be the mechanism that caused some of these abrupt changes in the past? We don't know. You know, there's some, we have some good theories out there that have to do with ocean circulation, that have to do with some with atmospheric circulation. It is still a question that we're asking. It is very challenging for models, for example, to make temperature change that rapidly and be that stuck, if you will. Keep in mind that for thousands of years you're cruising along in one state, then a very short period of time you go to another state. And you don't see a whole lot of attempts to get to that point along the way. So there's very strong attractors for cold and for warm on the planet. And I don't think we've fully identified what those are. We've still got a ways to go. Yeah?
Same sort of question. You mentioned a lot about the abrupt changes in Greenland, but are these also mirrored in Antarctica? Were these abrupt changes also seen in the Antarctica ice cores?
Not really, no. The northern hemisphere, being a land-ocean hemisphere, seems to have a lot more thresholds in the temperature climate system. We have a history of one potential abrupt change in Antarctica that has not been replicated. So the water hemisphere, the southern hemisphere, seems to be a much calmer place when it comes to climate change. Yeah?
Do you see any silver lining in the fact that we might be ending this wild oscillation of glacial and interglacial periods that has dominated the past couple billion years or so?
Yeah. Why not? The fact that I don't think it's possible for us to go into the next glaciation. And I don't think we ought to shy away from that. I don't think that, I mean, it's pretty clear that we did not start burning coal, oil, and natural gas with the intention of getting out of the next glacial. Right? But when you step, you know, in, you know what, and your shoe doesn't get dirty, you know, why not? That was a really horrible analogy. That was, with that horrible analogy, thank you so much.